us. All right, actually. All right, so it's 11 o'clock. Let's get this thing started. So if you're just now joining us, this is our H2S and CO2 removal virtual roundtable. This is us focusing on specifically getting a subject matter experts, coming together, talking about it, true applications, past experiences on focusing on H2S and CO2 removal. So some quick housekeeping. If something happens, this is on the internet. If you lose connection, kid walks in the room, internet goes out for some reason, we will be putting this on our YouTube channel and a transcript, so that way you can do a quick control search find. YouTube, LinkedIn, blogs that we have all of our information on. The speakers. So today I'm Chief Executive Officer, but only for today apparently. But Crop Production Systems, we're a natural gas processing company. That's what we focus on. I got my Director of Engineering joining us with Crop Production Systems, Chris Smithson. He has a lot of years of experience focusing on production and processing of natural gas. Jesus Oliveras is joining us. He has a lot of experience on the back-end design work for even in civil projects, but in oil and gas projects. And then now he's a CEO of his own manufacturing facility, Synergy. And we got Terry Nelson, who manages and runs a Waukesha, our WPI's division, focusing on dehydration, natural gas processing issues, JT plants. He's going to be joining us today. He has a lot of experience back Hanover, Exterran. And then so from these subject matter experts that we have joining us today, we're going to be focusing specifically for H2S and CO2 removal. So today's outline, quick H2S removal, CO2 removal, and then we do have a good case study at the end, kind of a focus that came from one of our people joining us today. He's from Australia. Now, the roundtable structure, how this is going to work, because not everyone can answer. So I'm going to be playing the host. I do got question and answer and the chat function up and running. So if in our conversation, if something prompts in your mind of having a quick question, or if you want confirmation on something, put it in the question and answer, or you can put it in the chat function. And then as soon as it comes back up, I'll make sure that question is trying to be answered as best to the ability as we can give it. So kicking this off, we're going to be focusing on natural gas contaminants, specifically again for H2S and CO2. And kind of starting this conversation off, what we did is I want to kind of quickly touch bases on the processes for acid gas removal. We only got 1 hour, but the first one is batch process. Then we're going to go into continuous injection, and then third is the regenerative process. So in this, kicking it off is the batch process. Now, the functionality of this, Chris, I mean, if you can kick us off of like batch processes, you got bubble tower, sulfur treat, but kind of go into your experience on that.
Yeah, so the main batch process is either a solid or a liquid that's going to remove the H2S or CO2. Molecular sieve is technically a batch process, regenerative, but it's technically a batch process. And usually you see that on big facilities for like fine tuning CO2 and H2S removal. Sulfur treat is a big one for, it's a solid black material that's shown there. They also make it in different formulations. They even have one that looks more like those beads. But sulfur treat CO2 removal. It also does other sulfur removals for different grades of iron oxide type media. Sulfur treat's just a trade name for one brand of product. But the other batch process you see a lot in the field is bubble towers filled with liquid scavengers, so the H2S scavenger that's filled up there, and it's just operated until it doesn't meet spec anymore, and then it's drained and refilled. So those are the kind of the main batch processes you see out there for H2S and CO2.
So to be a little bit more specific, let's focus on bubble towers. Like, what are the past experiences on bubble towers, especially like personnel issues?
So for bubble towers, I mean, they do have a good, fit for smaller well volumes where you're not going to be consuming that, scavenger. You have a consumable scavenger, eventually you got to throw it out. So the longer that's going to last between having to refill that bubble tower, is important. So smaller well volumes that aren't going to use up that scavenger, lower H2S levels, something in the H2S range of maybe less than 100 ppm on volumes less than 1 million. You know, that's a good range for a bubble tower. I wouldn't want to refill them more than once a month. They can get kind of tedious if you have a chemical guy going out there every week trying to refill them. But there can be higher H2S removals. You can definitely have some problems with the scavenger building up in there. And I'm sure Terry's had some experiences with seeing what that scavenger can do when it goes bad and you end up with those solids in them.
Yeah, you can, you know, the problems with the batch stuff, I mean, it's an excellent tool for, like you said, lower end process ranges where you have a minimal gas flow and your contamination levels not so high. But you know, the problem seems to be was twofold. One is getting rid of the batch product and having to, you know, either dispose of it and then of course financially keep replacing it. And secondly, and what I find is when people they don't have the forethought to make sure that everything attached to that vessel and in the line after it can handle the corrosiveness of what we're dealing with.
Mm-hmm.
You know, I've had customers where they repurposed vessels, you know, it's just a separator, so let's fill it with some stuff and let the gas flow through it, when they don't think about corrosion allowances and making sure that all the controls and instrumentation, including relief valves and everything else, are meeting the standards of what the product is now that you're dealing with. And
yeah, fit for purpose vessel can be a lot better. Yeah, we've seen some interesting retrofits. Jesse, I don't know if you've ever retrofitted vessels for like turn them into bubble towers or something.
Oh, I have, and I think one of the things that Terry was mentioning that you have a lot of issues with is, especially if you don't go through the proper cleaning process of getting rid of your old stuff, and it starts coking, and then that coking starts eating into your vessel and your material. And before you know it, if it just stays there, you know, a month longer than what it should, for example, then you're going to start eating up, and then it's going to cost a lot more money to replace stuff, and then you have issues. But just trying to modify something, you know, I'm one of those in favor of saving money. And if you're able to do it correctly, then yes. But basically, you're having to take something that was used for a different process, and you have to gut it out and repurpose it correctly into what you need now. You know, so I think that would be the key. That if you're going to repurpose something, make sure that you do it completely, not just, I've seen it where you have like, it was like into trays and got converted, but they didn't remove the tray rings. You know, they removed the trays, but not the rings. So all that was just creating a big time corrosion point, right? So I think it's just, when you do that, make sure that you do it completely, not just half, right? So.
Yeah, we saw one vessel that was a converted Molsiv vessel, and Molsiv, which is those little tan colored beads, they flow real easily out of a vessel. So like, I think it was like an 8-inch port or something, which is fine for Molsiv, but trying to get that sulfatreat, the standard sulfatreat isn't uniform in shape. It's like little crumbles, and trying to get that, you know, out of those tiny little ports makes clean out rather difficult. There's other brands of iron oxide that are round and they flow out better, and they don't clump or turn into concrete like some issues you can have sometimes with some of those sulfatreat options. But yeah, that can be problematic. And then even the bubble towers running the scavenger, if you don't have the right drains on them, maybe bigger drains, maybe some clean out ports. We've seen, you know, that solidification. It's when you overuse the scavenger, you get this yellow cakey material. You get two different types of byproduct from overusing scavenger. You get a soft, squishy material, it's like cottage cheese, or you get a very, very hard crystal material. The soft material can be melted out. If you run like we'll do hot water baths on our injection systems, and that'll melt the sulfur out. You know, run 200-degree water through it. But if that crystalline material, the only way to get that out is mechanically. A lot of acids won't even really get it. So that's really problematic. If you got just a little 1-inch drain on one of those vessels and you're having clogging issues, that's just going to give you a headache every time you try to empty that vessel out.
Well, for
Yeah,
like,
it reminds me, I think,
go ahead, Jesse.
I was going to say, it just reminds me of you know, when you're trying to clean some of these vessels and they're already all caked up, that you almost have to sandblast that thing just to get rid of all that. You know, so yeah, it's a lot of work to go after it's already all, you know, caked up, and then you're having to clean it. We've had to basically sandblast some of that stuff just to get it rolling faster. You know, sometimes you try to put some of these jet systems in there to try to get circulation going, but the bottom line is if you follow the right operating procedures and you have a good maintenance procedure, you should be able to avoid all those things.
Well, that kind of leads into one of the questions that we did receive. Like, what are some quick tips for bubble towers? That is there any like quick retrofits or something that y'all can go in, diagnose what they should add to the system just to kind of make their operational lives easier?
For a bubble tower, like if you're using liquid scavenger for a bubble tower, if you're having issues where it's getting used up and you're seeing that precipitate come out of it and you're getting that clogging issue, you're probably also refilling that vessel a lot and more often than you'd probably want to. I would say put some direct injection ahead of the system, try to get rid of some of that H2S. I mean, you're going to spend what you're going to spend on scavenger. You save money when you use it up so much that it creates that solid, but the solid's going to be, it's not worth the savings to have that much of a headache. But I would say try to get some scavenger ahead of it and separate it out. That way the bubble tower is not working so hard and you're not having to clean it out as much or refill it as much. And the sulfatreat, I mean, you can kind of do the same thing with a sulfatreat if you're really annoyed with how often you're filling it out or refilling it. You can try to maybe do something ahead of it and try to knock down the usage on that. Iron oxide is the cheapest way, pound for pound or cost. It's the cheapest way to remove H2S. It just can be a big headache to refill those things.
Yeah, I agree with all that. And I tell people, and it was mentioned earlier, do not let the stuff stay in there past its life. Mm-hmm. You know, all these things have a lifespan. Once the efficiency of what they're there to do has ran its course, change that stuff out. Don't, for economics point or whatever, let it linger in that vessel longer than its efficiency maintains, because what you're doing is that product is going to start solidifying and bridging over in that vessel, and it's going to be really tough to get it out, you know, and the longer you leave it in there past its point of efficiency, the harder it's going to make it in changing it out. And, you know, another thing is for the crews that go out and work on this stuff, and that's what our guys do, is just because you've removed the product out of it and just because you stop the gas flow going through it does not mean that you've eliminated the H2S in that vessel. That metal is very porous. The inside of the vessel will hold a lot of that H2S. You hit that with some hot water, and when you're going through the cleaning process, you're going to release H2S, and it's a definite hazard. So you have to make sure that all the PPE is followed, even if you're just cleaning it out. And the third one is any liquid drain lines that leave these vessels that go to a slop tank or to storage, in my humble opinion, should be an independent drain line. If they're tied into multiple sources, that product can migrate back through those dump lines and cause plugging that will cause the other vessels or blow cases that are trying to get rid of their product. It can cause a restriction in those lines, and then you'll spend days trying to trace it back and figure out what's causing the limiting of the other dumps from going through the drain lines.
Well,
Yeah, we've
Terry,
definitely seen that where we get like backlog of it'll shoot some of the solids down like a seldom used drain line, and then all of a sudden that separator tries to dump and it can't dump anymore and break a dump valve
Mm.
off, and somehow you have solids all the way back up to your trim of a dump valve that shouldn't be seeing any scavenger on the front side of it.
we do have a question. Kind of, Shane asked, do you recommend any additives to the Trizene H2S scavenger to minimize solid precipitation from the spent chemical?
So with the, I'm not a chemical guy. I've just talked to enough to know that I'd hate to be a chemical guy. So the Trizene, there's like 2 or 3 companies that actually make Trizene, like the base product. Everybody else, they buy it from the same people. So the base Trizene product, the way that works is it's a chemical compound. It can grab up to 3 H2S molecules. When you grab the third one though, there's a chance that it breaks off from the molecule and you get the sulfur actually is a free compound floating around where it can collect with the other sulfur and create the solid. So if you have the solids in there, it means that you're using it up completely. You're just living with that byproduct of you know, being that effective at what it can do. The only thing that I've seen, I mean, most people blend them with like a scale inhibitor and a corrosion inhibitor, or it normally is a corrosion inhibitor in its own right, the scavenger, but they'll add a scale inhibitor to keep any sort of scaling from forming in the pipe. But methanol is the only thing that I've heard. I read we had a bunch of problems with this when we were first getting in our chemical skids years ago. And we saw a lot of the solids build up. It does seem to depend on the scavengers. Certain ones are more likely to have that build up. We used to use one that smelled terrible before you even used it up, and that one for some reason really had a bad problem with the solid builds up. The normal Trizene, we use a fairly standard blend of Trizene, but adding methanol to it can help to keep the solids from forming. I read that in a research paper, and I've heard that from 1 or 2 chemical guys, but it can take a lot of methanol to, I don't know if it'll completely stop it from happening, but it's a pretty good idea to just have methanol mixed in there all the time, not just for winter to keep it from freezing.
Didn't we, Kristen, this is for that South Texas project where it started getting, that solidification started happening. Didn't we like lower the concentration of the Trizene as well, just to kind of make sure there's enough fluids that when it was dumping, it was properly dumping and cleaning it out?
Yeah, we normally would use like a 50-50 mix, so it's 50% water, 50% active chemical for in our units, because we're trying to treat within a skid unit. Direct injection, pipeline injection, the typical blend is a 25% active to 75% water. And so yeah, in that case, we did go to the higher water mix just to keep enough fluid going through there. We had to double our injection rates, but the chemicals almost half the price. They got to sell you water somehow. So that helped to just kind of flush things out, just because we're physically moving more liquid. It helped push more of the solids away. So yeah, that did help to go to that mix. So we had to add an extra pump and, you know, more batteries, more panels to power it, but it did help to keep that clogging down.
Well, flushing is the right term, you know, and that's why I mentioned earlier to have a dedicated dump line on this kind of stuff. But also what I've done is when it leaves the vessel and enters the line going wherever it's going for disposal or whatever, add a connection there where you can flush it occasionally, you know, and have it part of your PM process on a regular basis to either dump methanol into it or something, whether it's water, whether it's maybe tying off of another dump line and allowing that to blow through there occasionally, just to flush that line so you don't get that buildup. Because over time, the product, we have to remember, we're pulling sulfur, so you're going to get some caking of solids in that line. So if you flush it occasionally, that helps keep that stuff from building up and bridging inside that piping.
Well, that kind of goes into, we did have one, I think it applies mostly to this one, but they were having trace amounts of H2S before it hit their instrumentation and fuel gas. And they were just kind of wanting a quick cleanup, or even like a redundant vessel. What do we what do y'all find is the best way to treat for that trace amounts of like fuel gas and instrumentation gas before it goes in those lines? Is that a bubble tower or
Yeah, I think a batch process would work best for that. Usually that's intermittent volumes anyway, and batch processes are usually a little better at that. Continuous, you may end up wasting a little more chemical. But yeah, like I mean, sulfatrete's nice, or iron oxide's nice for intermittent flows and where it could, you know, varying volumes, because you're only going to use as much as there is H2S in there. Bubble tower could be good for that as well, but like Terry said, I mean, eventually if it sits there for a long time, bubble towers will pick up other stuff. Sulfatrete will too. It'll pick up other stuff. So you may end up having to clean it out before it really is time to do it, just because it's been in there for a year and a half. And if you don't do it now, you're never going to be able to. But I would go with the batch process on that, because at smaller volumes like that, you're not, you got to put a vessel out there anyway, so it's, you know, going a little bit bigger on the vessel, it's not that much more of a cost to have a little overkill in there.
Well, like on the offshore platforms that we maintained through the years, we would have an issue where on some of the platforms you would have a minimal amount of H2S, and we had to worry about it with instrumentation and panels and, you know, contaminating all that. And we would put a batch vessel there with like the beads in it, depending on the product, you know, it's different, but, and then that way it was easy to transport for waste disposal when we had to change them out. And it was also, it lasts a long time when you're only talking about a very small contamination level and very small amount of gas when you're talking about, you know, something on the inlet for controls and stuff like that. So it works really well using the batch.
Well, especially if you do a twin setup where one is always, you always have one as a backup. You switch over, you could dump one of them and operate the other one, so you're never shut down. Another idea, obviously, is if you're able to evaluate your design and whether you're able to do either a nitrogen little setup or something else that you would eventually not have to use your natural gas. So we're just looking at what would be more cost effective and what's more available at that time. But since everything changes, what might have not been a good idea at the beginning, down the road, you might reevaluate and go with a different option.
That's right. Well, we got another question that popped up. It says, can Terry qualify minimum amounts of H2S?
No. Well, I mean, I think that Chris mentioned that earlier when we were talking what we consider minimal amounts of H2S.
Yeah, I would say really you'd want to be something around like maybe 50 ppm. It depends on the volume. The volume in H2S is going to determine how much product you're going to go through. So, I mean, you may be 1,000 ppm, but all you need is an MCF. And so at that rate, you know, it's a lot of H2S. But if that gets you like a 2-month refill cycle, then you're pretty good. But if it's like 10 ppm, we were doing one application, it was 12 ppm, but it was 30 million a day. And so it was like 60 gallons of scavenger a day that we were using. So it depends on what that crossover is as far as what the usage is. Obviously, you don't want a tremendously large batch vessel just for, you know, 100 MCF a day in fuel or something. But it would depend on what that H2S rate is.
Right. And
usually it's going to be less than 100.
And what's the CO2 level? And is it dry? Is there any moisture? I mean, you could have a very minimal amount of H2S, but if you have moisture, that changes everything. So we have to make sure that is very dry fuel.
Yeah.
Or very dry gas.
And that also affects what you're going to use too. So if the gas is already dry, but it's got some H2S in it, if you put a bubble tower out there that's half water, then you're just going to resaturate the gas, and now your instrumentation gas is wet again.
Exactly.
Then you got to put a dehy out, like a little batch PDS vessel or something to dry it out. But then you're adding other problems. There's iron oxide ones that don't need wet gas. A lot of them do. I think most of the standard sulfatrete product needs water in the gas to work properly. You can't really run dry gas. They have special blends for it. But yeah, it can affect what you're, oh, let me just add a little bubble tower here and it'll be fine, and then all of a sudden you're having other problems.
Well, we did get a question coming up. I think it's going into the regenerative process. I'm going to scroll down, but it's saying, what are some other liquid H2S scavengers used for contact towers? How do they compare to trizene efficiency economics treatment issues?
So that'd be for like the direct injection or the CIS unit. So like so instead of trizene, what other options are there? So trizene's the most popular. I don't know how they quantify that. I mean, all the different people that use it all over the world and everything. But they say trizene's the most used consumable scavenger that there is. There's other ones. Baker makes a couple different products, but they have like an amine base. There's one that has formaldehyde in it. I just know that because it smells terrible. But it's not a trizene base. It's a converted amine that ends up with formaldehyde in it for some reason. Those aren't as effective as trizene. I think trizene's kind of won that battle as far as like usage for that. The converted amine ones also, they can have more issues with the solids as well. There's other types out there. That are like iron based, like a liquid that has a bunch of iron oxide in it. That can actually be regenerated. Or it can just be thrown away as a scavenger. It's a little pricier, but it's not trizene. I know some pipeline companies have issues with trizene. I can't remember offhand who it was, but we were working on an application where the pipeline company didn't want the trizene. Something to do with corrosion. I wasn't exactly sure what the reason for that rule was. But there's a couple other options. Trizene's just so common that it's hard to compete on price for anything else.
Well, hopefully that answered Shane's question. But you were talking about continuous injection, like into the tower. We've seen Polaris, Extern, Hanover designs. We got several bubble towers that we rent out. What's y'all's experience on that, where it's just liquid on the bottom, or we've seen them where they atomize at the top? Have y'all seen efficiency gains in the atomization at the top and then having it just settle out in the liquid on the bottom? What design do y'all like the most?
I mean, I think they each have their own benefits, but I mean, the atomization at the top, I mean, that has benefits that to me be more efficient. But then, some people will tell you that the bubbling, from the bottom is better, but I think it's just dependent on the chemical you're using and the overall rate of contamination and how much you have to treat to get out.
Yeah, the Valaris design bubble towers, they atomize in the top, and then they have the accumulation bubbling section on the bottom. They had a recommendation of like 2,000 ppm max, and I think part of that that shouldn't be a NACE function. Jesse would know better. I mean, I'm sure they could design it to handle higher H2S amounts, but I think that max was really more stemming from having to just inject so much scavenger into it that it's not really feasible to go higher as far as that. What's pictured here is our little CIS 100. It's for 100 MCF a day. We've actually treated 10,000 ppm with this, which is a percent of H2S for a fuel gas application for a generator. And I wouldn't say it's cost effective against diesel, especially with diesel prices now, but back when diesel was more expensive, it was at that rate, at that 10,000 ppm. But what this unit is, it's got an atomization injection, it's got a static mixer, and then we have the bubble tower. It's really more of a separator and finishing unit. Bubble towers are great at smaller volumes. I wouldn't try to treat 1,000 or 2,000 ppm through just a bubble tower, just because it doesn't have enough contact time. The Valaris design ones have the atomizers in the top, so it's constantly the freshest chemical in the top, and then it's going down to the spent chemical. So they do use it up a lot, but real high H2S rates, you're not really going to want something that's just churning in there, because you really need to start getting that scavenger out of there, or else you can have some problems with it. The ultrafab units are a little different. The ultrafab units have they're running it through a contactor system. So they have like a pack tower, and they're running it through that tower. But it's the same problem. Real high H2S rates, you can end up with clogging. I've heard horror stories from techs talking about trying to clean out those ultrafab units so that they just get completely full of sulfur. But that can happen on any bubble tower system.
The biggest problem is when is a misapplication. When you use a vessel that was designed for a certain application, a minimum contamination rate or a minimal flow rate, and you put it in an application that doesn't meet what it was designed for, it's never going to end up well, because you end up with a vessel that you either have to change out the product more often than you should, or you get the plugging and you have all kinds of problems because it wasn't designed for the application that it's put into.
Well, like you were saying, Terry, we on our first design of this chemical injection skid, we started building the bubble towers. Well, we had the drain port and the level controller approval set kind of at the bottom where you were first draining out from the bottom. And what we were finding out, there was so much condensate that was coming in, so the condensate would start filling it up, and it was practically just kind of like it was floating, on top of the scavenger, so it was pushing out. So we were actually draining out the scavenger. So by the time a few weeks went by, our thing was full of condensate, but it wasn't full of scavenger anymore. So then we started draining at a higher port, so that would trigger from that, and we were approval draining off the condensate off top. So there's a lot of quick tricks that, you got to have, it has to be applied to it.
Which goes back to the point of when people are repurposing vessels and just taking a separator and putting it on a skid and adapting it for a bubble processor, the connections are not going to be in the right place.
Mm-hmm.
So there's a learning process.
Well, Jesse, you don't have to have any of that with your customers repurposing, right?
Well, and I think we've had a similar conversation in other of the webinars we've had, and it goes back to understanding, and Terry brought some of that up in this webinar and so forth, that, understanding the conditions, especially, skid packages, it's so easy to move them from one place to another that if you assume that, if it worked here, it's going to work over there. Well, that's not the case. You need to really understand the conditions, because you might have the same gas flow, but what if you have a different liquid, different component composition, all those sort of things that if you don't reevaluate that, you're going to end up having issues no matter how good the equipment works.
We got a question for a contact tower, but I'm going to leave that for the regenerative process towards the end. But I kind of fall back onto my dad. He was an operator, consultant operator, so he was on a bunch of fields. And one of the biggest things that he saw on the expenses was the chemical usage on the location. So when he started consulting out there, he started documenting, chemical salesmen, they get a bad rap because they're water salesmen. That's, everyone keeps popping on that. And you get good chemical salespeople that honestly want to do a good job, but if you don't give them the right data, they don't know how to respond with the right chemical. So my dad started focusing on that, and what he found out his client was doing just like drip injection, continuous injection, but it's just drip injection. They were using all the 90s and 180s and coming back and trying to make contact time. So he took those out and just put atomization in there. And what he claims, now it's my father, he tends to lie to me a lot, but he said he claimed that there was a 20 to 30% drop in chemical usage just by putting the atomizers, and for getting better contact time rather than relying on drip injection.
But that depends on if you're buying the chemical or you're selling the chemical.
Right. Right. Yeah, it could be that too, right? Well, was there quick tips that y'all have seen in the past that operators are resourceful. So is there anything that y'all saw that was kind of a cool best standard practice?
It's all about, it's atomization, no doubt, but it's where you do it. You have to find an injection point with a certain amount of straight pipe so that you can get the mix going, and the atomization has to occur down a straight piece of pipe. If you have too many 90s and stuff in a connection, a length of pipe with too many bends and turns, that's not the place you want to inject it, because you're not going to get a good mix. That atomization is going to be spoiled because of all the twists and turns. You have to atomize it at a point where you get the benefit of a straight piece of pipe. That's just the tip that I have done in the past to find it works well.
Yeah, I think that's true, and because an elbow will knock out a lot of chemical, like a lot of it when it just the shear stresses of the gas going through there just throws out the atomized stuff. So yeah, Terry's right on. You don't want to inject right before a bunch of elbows. You want that nice long run where that atom, that fog that you've created can go through there. That's another tip. There's a difference between a mister and a fogger tip for atomization. You want an atomization tip that's like really making real tiny droplets, because you're just getting more surface area that way. You don't want something that's just gonna like mist in there and like big old heavy droplets are gonna fall out real quick.
Right.
The finer tip that you can put on there, the better. Which means you got to filter good your chemical, or else you'll clog up the tips a lot sooner. But the other thing is the stuff's gonna, it's gonna do its job. It's gonna remove the H2S. It's gonna fall out eventually. So you do want a separator downstream of that, but you don't necessarily want that separator too close. If that mist that you've created is getting knocked out in your separator, that's good. You want that to happen. But if you have a mist pad and not a vein pack in that separator, and that scavenger is building up in that mist pad, collecting and then dripping back down, you may have your solids problem occur in that mist pad. So then now you have a mist pad that's full of sulfur solids in there. Whereas if you've given it more pipe run, and then maybe hit that area with all those elbows where that's getting knocked out after it's done its job, then you're having more of a free liquid hit that separator, and hopefully it's not getting stuck in the mist pad. Because we've had that on units. That was our mistake when we first started building those CIS units, was put mist pads in them and not vein packs, because it makes them a lot harder to clean when you're trying to get cottage cheese out of a bundle of stainless mesh.
I guess the mist pad was doing its job, wasn't it? It was basically coalescing.
Yeah, I mean,
so
it works too. Yeah, it's giving you surface area. The liquid's totally coated it, so it's letting it pull the H2S out. But when it came time to clean it, it makes it a much bigger problem. If you ever see a differential on something like that, I mean, that the differential is most likely in the mist pad. Like if you're injecting scavenger and you're having that problem, that's like the first place, because that's the tightest place on the whole thing. So we've seen that on sites where they're injecting scavenger and they have 15 psi differential across their separator, and it it's really a red flag if they're seeing that.
Well, that kind of goes into, before we move on to the regenerative process, there was one, they didn't mention either water storage or oil tanks, but they were saying that there was H2S being liberated in the head of the tank, at the top of the tank. So they were trying to figure out, I was going to, they didn't mention a vapor recovery unit or anything, but how would y'all go about treating for H2S that's at the head of the tank?
So I think a cool trick that we saw from our local chemical guy was that they were atomizing into the head of the tanks. I thought it was neat. They just took out a bolt out of the thief hatch flange bolts. They took out one bolt, put a bulkhead tubing fitting, and then they put the atomizer in on the inside of the tank, so you could really easily change the tip if you needed to. But they were knocking down a couple thousand ppm of H2S just by fogging that headspace of the tanks, and which makes it so much safer for the guys that if they actually had to pull a gauge on those tanks, you're not opening up a thief hatch with 1,000 ppm, because it will concentrate in areas like that, especially in the heat of the summer. It'll liberate out of oils or gases. It's H2S is kind of weird. You could have oil without really any H2S and a gas full of it, or you could have gas with a little H2S and then really high H2S levels in your oil. And you would need two different scavengers to properly treat those two different strains, because the oil scavengers and the gas scavengers don't quite work as well interchangeably. But yeah, treating that gas headspace can be pretty effective.
What we've done, is that's always an excellent idea, to have that misting right there at the thief hatch. What we've also done is on the piping of the tanks as it enters the top of the tanks, we've put a T there before with a valve and piping away from the tank so that when an operator goes up to have to gauge or whatever, he can manually vent before he pops the thief. And then he's blowing that high concentration out away from him. Then he can relieve that thief hatch pressure, which has basically already been relieved because he vented it out. But it's all a matter of awareness. You know, if you have a high H2S application, just because you're treating the H2S with a bubbler vessel or an amine plant or whatever, you have to know that everything on that location is always going to have H2S. You know, whether it does or not, you have to consider it that it does. So you build procedures in place to protect your personnel. And so we've always, when we built a tank battery on an H2S facility, taken into consideration the truck drivers that come in, and they may have to vent tanks or whatever. Sometimes they have to open thief hatches to pull on tanks and stuff. Just to have a procedure and a tag or a sign that says, you know, open so-and-so valve to relieve the pressure and then pop the thief. You know, that way it's not coming right up in your face.
And I think other things that have been added are engineering controls, maybe put in, instead of trying to go in there and gauge your tank, maybe having some electronics or, you know, some level gauges that are able to tell you more of your levels instead of, I agree with Terry. I mean, when it comes to H2S, the last thing you want to do is the least, I guess, human contact you have with it, the better you be. So anything you could do to avoid that, that would be what I would consider, you know, first. So being able to look at it from what the outside, either electronic or some kind of side glass, and then of course we talked about already some of the atomizing inside. These to protect that. So there's just levels of protection that you want to make sure you have for your employees or anybody gauging.
Didn't even think about that nowadays, you know, with Murphy gauges and all the advanced level detection, the sonic stuff. You know, there's ways that you don't ever have to even climb a ladder, I guess, to even gauge tanks anymore. But I'm old, so I think about, you know, dropping a gauge in them.
That's what's scary when you go to some locations and they don't even just save money. They don't even have the flag that's in the corner to see where the wind's going. Those are the type of locations you really want to make sure you have your monitor and escape pack and a buddy.
All the H2S driving up, but you don't see any signs or anything.
Yeah.
I remember they issued all the technicians one time early on when we first came up, before everybody had the Scott air packs and everything. They issued these 5-minute evac packs. And it was basically a plastic bag that you put over your head, and it had a little oxygen tank attached to it. And you had to test them every so often to feel confident with them. And you had these guys on location with plastic bags over their head running around. It looked pretty ridiculous.
Yeah, that was pretty bad. By the time you got from the top of the stairs at the tanks down to the bottom, you had already used up all the oxygen.
Yeah.
So,
the bag fogs up too, and so it's just like a fishbowl running around.
Well, we were doing a training session, and one of our guys, he was an older guy. He was a mentor to me. He was a Cajun, but they were talking about the buddy system. And then they said, if someone passes out on a known location like that and they fall down, you do not go and get them because it might be a pocket of H2S that they're running into. You call emergency services, you back away from, so that way you have something. And then they said, John, you wouldn't come after me? And he goes, no, sirree, I'm not going to come after you.
It's funny, but on a rig that I worked on offshore back in the early 80s, they had 3 guys that died in a bilge tank.
Yeah.
Because one guy went in and there was low quality air, so he suffocated. Another guy went in. 3 guys went in before somebody said, stop going in.
Well, that's what they were saying is your first response is to go in and help them, but they don't realize that you're the lifeline. You got to back away so that way you get proper people in that area.
That's right.
But to move on, the last big section is the regenerative process. So amine plants, and I know our company sells and rents these amine plants. And Terry, you've worked on amine plants, and Jesse, you've built amine plants. So in this case, we actually had one question I do want to get involved in this. It says, what gas velocities are you targeting for the contact tower? I've seen 0.12 feet per second for unpacked towers, as high as 0.5 feet per second for packed towers. So
I think you may actually be talking about bubble towers and for like scavenger.
Okay.
Some people build them out too. They'll just take a contact tower and they'll just run it like a circulation pump, and they'll just keep pumping the scavenger through like a bubble tower or a pack tower, and they'll use that for contact instead of actually bubbling. The benefit is you get a smaller tower at higher velocity, like he's saying. But I had to do the math because I'm usually looking at the feet per minute. But yeah, 0.12 feet per second, it's about 7.2 feet per minute. I've seen 8 feet per minute. That's probably the standard. It's in the textbooks as far as like the old school methods for liquid bubbling. I forget what they called it. It was a Schlumberger process or a Baker process, like a powder you had to mix with water, and you threw it in the tower and it would bubble. And those are all recommended at 8 feet per minute, which would be about 0.13. And yeah, you really want to go above that. You could probably push it maybe to 10 feet per minute, but then you're looking at potentially carryover. And then it gets into how did you design the vessel? Like, where's your liquid level? How much disengagement space do you have? Do you have a mist pad or a vane pack on the top? And, what's that distance between those things? So if if your outlet is a foot away from the top of your liquid, then you probably want to slow it down even more than that. It kind of gets into the design. The other number for the tower, for the unpacked tower, or well, I guess for a packed tower, if you're actually running like structure or random packing in a tower, 30 feet per minute, or the 0.5 feet per second. You could run like amine numbers for an amine contact tower. It's like 40 to 45 feet per minute. Is the recommendation not to exceed. We usually don't exceed 40 on ours, or else you start getting carryover at the top of the tower. But yeah, you could have if you're not atomizing, if you're atomizing in a tower, you want to slow it down, or else all that mist just goes right out the top. But if you're just dumping it into like a pack tower and you're letting it dribble down through that packing at 30 feet per minute, you can probably get up to 40 feet per minute and still be fine. But again, it goes into what kind of tower you have. If you're surely just taking an amine tower and then just pumping scavenger into it, and you're just playing with just the tower, then you could go up to that 40 feet per minute knowing it's designed right. But if you're trying to like remake something and you've cobbled something together, it kind of depends on what that design is.
All right, well, that's on, so on the regenerative process, Ahmed, we don't got too much time left, but on an amine plants, I guess everyone's always looking for like good, quick tips to look after. So if y'all can, what are some good tips that y'all seen in the past for existing equipment or even new builds?
Well, to me, it's temperature. We have to maintain a reboiler temperature that is in a range where you're getting the process that you want, but you're not using so much water that you have to constantly be adding water to the equation, and that affects cost of processing. Whether you have a steam generator or you're adding distilled water, that's affecting the cost of processing. And so many times you either have a tower that's too big, or you have your pressure and your temperatures misadjusted, and you're affecting that, throughput through that tower, and you're either pushing water over the top, or you're cooking off so much that you're having to add so much water, it's affecting the cost of processing.
Well, you're mentioning the still column, so we did have a question come through. It says, can you explain briefly what is the function of the still column and the reflux condenser?
So go ahead, Terry.
Yeah, go ahead, Chris.
Oh, okay. So yeah, for the amine process, it's a regenerative process. You're using amine that's going to grab it, and you got to boil that CO2 or H2S out of there. Amine's great for bulk removal of H2S and CO2, just because it is a regenerative process. You don't have such a high consumable. But like Terry's talking about, the consumable cost can really eat into your operations if you're not paying attention to your temperatures and your water use. But you're boiling the amine, which is, depending on what you're running, if you're trying to remove CO2, you're most likely running MDEA. So you're probably running like a 40, 50% amine to water mix. So mostly what you're circulating is water. So you got to boil it out. The heat, when you heat it up, you'll release the H2S, CO2. Still column's going to help with that release. It acts kind of like a heat exchanger for the steam to counteract with the amine that's coming into the tower to boil it out. For this small plant like this, we do random packing. Bigger plants would be like a sieve tray or something on that. But really, it's to get the CO2, H2S out, and then the reflux condenser is to save that water that you've now turned to steam, so you can recondense it and put it back into the system. On a little plant like this, it's an ambient cooler. On the bigger plants, it'd be a forced air cooler. But yeah, if you're not watching your temperatures, if you're running a little too hot on your outlet of that cooler, then you're just sending that steam. I mean, you're just humidifying the gas that's going out, and you're just sending that out, and that's all water you have to replace in the system. Because of the heat of reaction with amine, when you're removing CO2 or H2S, the outlet gas is going to be pretty hot out of your tower, so that's going to suck water out of it as well. But also you're going to boil out a ton of water when you're heating that low pressure gas up, and a lot of that water is going to leave with there. So you're constantly adding water back into the system.
Well, Jesse, if you don't mind explaining kind of like the contact tower, that's the only thing that really touches the gas that you're processing. So is that the only vessel that needs to be NACE, or is there, like, would you recommend other vessels on there to be NACE?
Oh, no, I think anything that's going to have any of the risk side of the gas. I mean, you got the tower, you're going to go into your flash separator, you're going to have that. Anything going all the way through until you're able to separate that, where once it bowls out, even going through the steel column, I would still think you would want to really consider that, although you're at a maybe low pressure and what have you. So the next side for me, you're really just trying to protect, make sure you don't have anything that's you're either going to have stress cracking or you know, you're going to have anything eating up any of your wells, your material. It's very interesting material, and it depends where you're getting it from as well. What I mean by that is it domestic or from you know, Western Europe? You know, just because it has a certain spec, what we've seen is it doesn't mean that it's going to really hold up. We've had some material that was NACE certified, and still, I mean, when it came back as you know, our relationship with the customers, it came back and H2S was eating some of that walled internal material. So, you know, even when you try to protect the whole system, you're still having issues with that material. So I think it's always important not only that you're meeting NACE, but you're also inspecting your equipment. And I'm sure, you know, you guys have your own equipment, and Terry's definitely involved in it. And what we keep learning is, you know, you can't assume that everything is working so perfect that if you don't, you have to have that preventive maintenance in there, and you have to be checking, you know, whether the walls of it, whether you're having any contaminants going downstream, you know, whether you have scaling or any of those sort of things happening. So at the end of the day, I would consider most of the amine unit as a NACE unit, just to, for one, it gives me at least a little bit of peace of mind that, you know, I'm following all the base materials. And then in addition to that, we have our maintenance program and what have you to make sure we're protecting ourselves.
You know, what I tell people is, and when I do training classes, I always try to break it down to the simplest terms. And I tell people, when you look at an amine plant, sometimes you're intimidated by all the stuff that's on the skid. But if you think about it, the contact tower removes the H2S from the gas stream. The steel column removes the H2S from the amine. So if you think about it like that, you're sending the gas through the tower and you're sending your lean amine through the tower. The amine's falling down through there and stripping the H2S out of the gas stream. So now the gas leaving the contact tower is clean. It's sweet. So now your amine is heavy laden with H2S. So you send it through the steel column while you're sending steam up through there. The steam is going to strip the H2S from the amine as it falls back in the reboiler. The steam comes out the top of the steel column, goes through the reflux coils, where, like Chris said, you're getting as much of that water back as you can, and then the gas off of there goes to flare because it's heavy H2S. So it's a pretty simple process when you break it down to its singular components.
Well, speaking on that, we had some questions. So what happens to H2S or CO2 once it's separated from the amine? Where does it go? I know you said flare, but can you all explain a little bit more on what is that byproduct? You know, CO2, H2S, where does it go after that?
So you've heated up the amine enough to release the H2S and CO2. There'll also be a little methane in there because you'll have some methane entrainment that just got stuck with the fluid when it went there. And so you're boiling that off, and you also have steam in there as well. If you're targeting H2S, you're still going to get CO2 removal unless there's no CO2 in the gas. When your amine plant absorbs, it'll react with the H2S first. But unless you've done something pretty creative with your contact tower, you're going to start absorbing CO2. It's a slower reaction with the amine, but you still are going to absorb it. So if your target is like 4,000 ppm H2S that you need to remove out there, and the amine plant's the cheapest way to do it, you're probably going to get a lot more CO2 than that absorbed out of that as well. Like I said, unless you get creative with your contacting. So you're going to boil that out. So you're going to have this super sour mix of very low pressure gas. So unlike a glycol unit or most smaller glycol units, we don't operate the reboiler under really any pressure with the glycol. An amine plant will be under pounds of pressure typically. Sometimes with the BTEX you have like a little bit of ounces of pressure, but the amine plant operates under some pressure to help push things through the still column and the cooler and everything. But you have this really low pressure gas coming out that's like 60% CO2, maybe 30% H2S, and then the rest is like methane. So you have this really low pressure steam that's maybe not, you know, if it's got enough H2S, it's flammable. But you got to do something with that. So like Terry said, they sent it to flare. If it's H2S though, you do have an issue with flaring it, because if you burn it, it turns into SO2. SO2 is its own emissions problem. It's better than H2S as far, well, it's safer in the immediate term, but SO2 is considered a carcinogen, so it'll cause cancer. So you can't do it within like X many feet of people's houses. So that's the major downside with H2S removal with an amine plant is how do you deal with that byproduct from there. So a flare combustor, you can get like super high efficiencies on a thermal oxidizer where you're going to destroy the H2S and the methane, but you're going to have this SO2 problem. Like we did one application where the flare stack was going to have to be over 200 feet tall just to get the dispersion right from like burning it, that it would like disperse enough so that because it was like a house within like 10 miles or something. And so it would be, and that's what killed it. The flare was going to cost more than the amine plant was. Other issues, some of the bigger plants, like the big amine plants that do have a lot of H2S, they'll have like a Klaus unit after them, and they're actually converting the H2S into raw sulfur, and then they'll give it away because sulfur ain't worth nothing right now. But they end up with just piles of just raw sulfur. There's other plants that they have some add-ons to amine plants, like little additional things that will do a similar thing without the complexity of the Klaus process, that use like these consumables that can absorb that H2S and create like sulfur cake or something like that. But that's the big downside to H2S removal with an amine plant. I've seen the other question, like if you had a disposal well would be great. The problem is that it's coming off that amine plant into super low pressure, which actually kind of goes into Patrick's question that he submitted early, is that an amine plant would be the default. He has a bunch of CO2 that he needs to remove from a well. An amine plant is going to be the default because it's going to be cheapest bulk option to remove CO2. The problem is that CO2 is now 2 psi, And so to recompress that to put it in a well is going to be super expensive because I mean, if it's 30 PSI, that's not too bad of a compression, but 2 PSI, that's a lot of horsepower for such a tiny amount of volume, and that can get pretty expensive.
Yeah, well, we can leave that as the last question. So we had one of our people joining us. He's from Australia, and he actually had some CO2 issues. So, Chris, can you quickly give us just a brief background on what he's looking at?
Yeah, so he sent a wonderfully long email. It's awesome because it's got all this background information. It's an interesting story. So they have this well where they have a lot of gas that they used to use for fuel, but it's 40% CO2. So they had a custom power plant that could use that fuel at such a high CO2 rate, which is smart because you can send it directly in there. You're not really treating it. They probably had to do some dehydration or some basic separation, but it's basically going right into the plant. That's really cheap fuel. But then they switched it over because the well wasn't reliable enough to be the fuel source. So they switched it over to run on normal gas, which is 95% methane at least. And so they can't really use this gas anymore, but they love to supplement it. The problem is if you try to remove 40% CO2 out of that gas stream, that's a huge emissions problem. So he's saying that it'd be basically a million cubic feet a day of CO2 that would be released. So if you were to put an amine plant out there and you could actually bulk remove that much, then you would have quite a lot of the CO2 emissions off that stack. I mean, obviously CO2 is not nearly as bad as H2S when trying to deal with that. But obviously, different areas, that's a huge emissions problem that you might have. So the idea is, can it be injected in a well? The problem is, a million a day at 2 PSI, that's a lot of compression requirements. And that's a very large custom CO2 compressor that you would need to be able to re-inject that downhole. So he's asking about, is there any other CO2 options, removal options that might work that could keep it at a higher pressure so they don't have that compression requirement? And so for CO2 options, amines usually your default. Membrane will also remove CO2. It has a similar problem where you need that pressure differential to be able to separate out the CO2 through the membrane. So typically membranes, the big problem with membranes is they have a lot of waste gas that goes away with whatever you're separating. So for CO2, you're going to lose like 20% of your gas stream. That is like the methane part with it. So, but for this application, it actually might work because you're just re-injecting it downhole, so it's not really an emissions problem. But the problem is you do have a large pressure drop across that membrane.
Well,
so
we've seen that in the past, right? A couple of companies we were dealing with, they were talking about re-injecting the CO2 back downhole, almost like creating a CO2 flood. So their byproduct waste stream, the CO2, and they were just re-injecting it, right?
Yeah, I think his idea is more sequestration of the CO2, not so much like enhancing the oil recovery by using the CO2 to promote oil production. I think it's really just like, let's put it underground so we don't have this emission problem. And putting it back in formation, it's, you're not going to hurt nothing putting it there. But yeah, a membrane may help with the outlet pressure, because then maybe you can tweak the operating of the membrane. Maybe you're outputting like 100 PSI, maybe 200 PSI, which you still need compression for that, but the compressor just probably gets like half the size, maybe, because the compression, the hard part, it's an exponential curve for compression. It gets easier the higher the pressure it is. So that, a membrane may be an option. The other thing would be a mole sieve. Mole sieves are great at removing CO2. They can remove it down to like tiny amounts. But that's a pretty big mole sieve to remove that bulk amount of CO2. And then mole sieves typically would do a pressure swing to get that CO2 out of the mole sieve. So you absorb at high pressure and then you depressurize that vessel, and the CO2 will go out of it due to partial pressures between the depressurized gas and the high pressure gas. That's typically to do a pressure swing to get that CO2 out of the mole sieve. You can't do a pressure swing with this because then you lose all your pressure and now you have low pressure CO2 again. But you can potentially do a temperature swing absorption with a mole sieve. I actually looked it up before this because it was such a curious application for it. There is ways to do it. There is some people that have done that. It would take some. We don't do mole sieves ourselves. We have a partner that would have to do that on that end because it is a little more involved engineering on that side of things. But temperature swing absorption could be a potential thing. You would need a heater to flow enough hot gas over it to get that CO2 to leave the mole sieve and then send that at high pressure away back to the well. There'll probably be some gas losses with that, with the regen gas and everything. But it could be a way to keep your pressures really high, high enough to maybe not need compression.
Well, there was yeah, to kind of wrap that up. I mean, I was reading on UK, they actually had the same thing. They had a power plant that was running, so they actually ran a CO2 line back dedicated to it was like 30, 40 acres of greenhouses, and they were actually flooding, like almost CO2 flooding the greenhouses. So it had that rich, fertilizer environment, and they saw a 30% growth rate. So I thought that was fantastic. That was their way of solving it, was actually shipping it to a greenhouse.
Yeah.
But
yeah, Australia, I don't know if they what their greenhouse environment looks like.
Australia,
you have to worry about heat too much, or I don't think it gets too cold there to freeze the plants.
Well, you can do like hydroponics, aquaponics, or something like that.
Yeah, yeah. But a compressor may be a little cheaper than that.
Well,
it's an interesting application. But yeah, Patrick, we'd definitely love to talk to you more about it. See if there's something that we could help you out there.
Well, to wrap this thing up, because it's getting into everyone's lunchtime, so everyone's going to get upset. All right, so if you're interested in being a webinar speaker or know of someone that would be a good fit, please let us know. We'd like to, our marketer, Tori.Balagura, she'll reach out to you, talk with you, try to get you to come on board. Now, you are going to be getting a survey. So we're a Six Sigma company. We love ISO, but we, as us as speakers, we like spending the time, but we want to make sure that our information is coming across properly. So please let us know that feedback. You'll get a free hat or shirt to you, but it will help us kind of tailor this thing in the future. In the future, contact information, you can reach out to me on LinkedIn, info@crosssystems.net. All of that information will come to our organization, so that way, if you have back in where you would like for us to do more specific with your clients, or just you and your team in general, we'll set up conference calls. Terry has 3 to 4 of these webinars a week that he does. Jesse does his own webinars. So just let us know. We'd like to help you and assist you as much as possible. And at this time, I'd like to wrap it up. So Terry, Chris, and Jesse, thank y'all again for coming on board with us, and then actually joining us next month for our next webinar.
My pleasure.
All right, guys.
Thank you, Cameron.
Well, let's go get some lunch. So y'all take care. Bye.